Suppose we have two linear transformations, say T that goes from Rn to Rm, and S that goes from Rm to Rk. So in this case, it would actually make sense to compose these linear transformations, right? Because if we started with a vector in Rn, then T of v, right, when you apply T, it transports you from its domain to its codomain, so T of v is in Rm. But right, if T of v is in Rm, then we could use S to transport it from Rm to Rk, and so that means S of T of v is in Rk, and S of T of v, right, that's S composed with T applied to v. So S composed with T is a linear transformation. Or it could be a linear transformation, I guess is the right thing to say, because it starts from Rn and it goes to another Euclidean space. But the question is, does it satisfy the characteristic property of linear transformations? Well, let's just check. Let's take two vectors, say v1 and v2 in Rn, and let's take two scalars, a1 and a2, in the real numbers, and let's just check what is S composed with T applied to a1 v1 plus a2 v2. Okay, well, the only thing we know about this composition is that it's S of T of whatever, so let's write that out. S of T of a1 v1 plus a2 v2. But look, T is a linear transformation, so we could use the linear transformation property. We get S of A times T of V1 plus, A1 times T of V1 plus A2 times T of V2. Okay, but now look, inside of S we have another linear combination. We can use the characteristic property of linear transformations for the transformation S. So that gives us A1 S of T of V1 plus A2 times S of T of V2. But, of course, this is just another way of saying S composed with T applied to V1 plus A2 times S composed with T applied to V2. So you see that the transformation S composed with T is linear. It satisfies this characteristic property of linear transformations. So S composed with T is linear, but that makes you wonder. I mean, suppose we knew the matrix for T, suppose it's A, and the matrix for S, suppose it's B. If S composed with T is a linear transformation, it has its own matrix. Maybe we could call it C. And it seems like C ought to be some combination of A and B. And in fact, there's only one possible combination that it could possibly be, just looking at the sizes. A, because it's going from Rn to Rm, A has to be M by N, and B has to be K by M. And so really the only possibility for C is that it's B times A, right? C is going from Rn to Rk, so C has to be K by N. And this matrix product, it's K by M times M by N. You can see that matrix product is going to produce the correct size. But, so this is the only thing it could be, but is it this? Well, the short answer is yes, because when we defined matrix multiplication, we defined it specifically to make this true. So there's nothing to prove here, right? This is proof by definition. We defined the matrix product specifically to match the composition of linear transformations. So there's nothing to prove here. This is true, right? We don't need a question mark. This is definitely true. But knowing that this is true, so matrix composition of transformations corresponds to multiplication of matrices, knowing that that is true can help us understand a lot of things about matrices. Here's just one example. A lot of things about linear transformations. Here's just one example. Oops. So let's think about a matrix that's represented by an a transformation that's represented by an invertible matrix, right? So suppose we have a linear transformation that goes from Rn to Rn. That means its matrix will be n by n. What happens if that matrix is invertible? So this A inverse exists, right? So I mean, what would you guess? If you have an inverse matrix, how could that possibly be related to the transform that we came from? Well, it seems like the obvious guess is that A inverse might be the matrix for T inverse. That could be. Well, actually, this would be a little surprising because we don't even know if T inverse exists, right? T is a function. It's a function from Rn to Rn. Not every function from Rn to Rn is invertible. But, if this is really true, if A inverse is a matrix that represents an inverse function, then not only is T an invertible function, but its inverse is actually linear, right? So let's check. Let's check if this is true. So how could we do that? Well, right, we don't know what T inverse is. That's the problem. But we do have this inverse matrix. So let's define a linear transformation S from Rn to Rn. Okay, and we're going to define it using this formula. S of V is A inverse times V. Now the question we have is, are T and S inverses? Well, let's check. How do you check if two functions are inverses? Well, you compose them and see if you get back where you started, right? So we're hoping that after we do some sort of calculation, we get back just the vector v. So let's check. So t composed with s, that's t applied to s applied to v. But what is this? I mean, the only thing we know about s is the formula for it, which is right here. So this is t applied to A inverse times v. And then, well, what is t? Well, we know the matrix for t. It's A, right? So this is A times A inverse of v. So, but A times A inverse of v, that's the identity of size m times v. And so we're done. So t composed with s really is, t composed with s of v really is just v. I guess maybe a shorter way to put this was, right, we said we know that composition of transforms corresponds to matrix multiplication. So we could have just written, all right, t is really multiplication by A, s is really multiplication by A inverse. This composition turns into matrix multiplication, but that matrix multiplication just gives us the identity, right? I sub n of v, and that's v. Okay. Well, actually, we aren't quite done, because to have a genuine inverse function, this isn't the only thing that has to be equal to the identity. The other composition has to be equal to the identity as well. But showing that this is v is basically exactly the same, right? The matrix for s the matrix for s composed with t is the matrix for s, which is A inverse, times the matrix for t, which is A. But those together just give you the identity matrix of size n, and so we just get v. And so that composition also just gives us v back. And that means three things. Three things. It means that s really is the inverse function. In other words, t is an invertible function. It means that, so that's the first thing, t really is invertible. The second thing is that T inverse is a linear transform, which isn't totally obvious. And the third thing is the matrix for the inverse function, T inverse, is the inverse of the matrix for T, which, you would hope is the case, and it is the case, right? That's the nice thing about linear algebra. A lot of things that you hope would be the case are the case. All right, so let's look at an example of this. So let's find a formula for the inverse of this linear transformation. You could do this purely algebraically, but it would be a real pain, and we have a nicer way. So one thing to notice about this linear transformation, I've written it just as some big output vector formula, but actually, if you look at this formula just right, you'll see that it's the vector AB times the matrix -1, 3, -2, 5. So that means that this matrix, let's call this A, this represents T, the linear transformation T. So if we want to find the inverse, we just need to find the inverse matrix for A, because A inverse represents the inverse function, if there is such an inverse function. If T isn't invertible, then when we try to find A inverse, we will fail. But we can at least try to find the inverse. So let's see, -1, 3, -2, 5. Augment with the 2x2 identity. And do our row reductions. So I guess let's do row 2 minus 2 row 1. So -1, 3, 1, 0. And then 0, so I'm subtracting 2 times row 1, so it gives me a -1 here, -2 there. And now I can take row 1 and add 3 times row 2, I guess. So that's going to give me -1, 0. Let's see, this plus 3 times that, -5. 3, -3, sorry. Nope. No, plus 3. And then 0, -1, -2, 1. And then I just need to switch the signs on the rows. So 1, 0, 5, -3, 0, 1, 2, -1. And now this is A inverse, right? So now we can write a formula for the inverse matrix, or for the inverse linear transform. The inverse linear transform is just this matrix, 5 -3, 2 -1, times your input vector, AB. And then, depending on what you're doing with this, you might write this out. So this is 5A minus 3B and 2A minus B. So there's a formula for the inverse transform. And you can see, using what we know about inverse functions and the correspondence between linear transformations and matrices, calculating this was actually pretty straightforward instead of a big mess of algebra.